Good afternoon. This is Algebra 571, 572, so the graduate sequence of algebra, and it will be a two-semester course. So the first semester will be Algebra 571. I will go briefly over some of the remarks and comments of how the course is organized, and then after that we will get to the topics that will be covered in this course, and then start with the first lecture. So to find more material on this course, basically you can do this through my website. So the website can be found either through the Department of Mathematics, or you can do a search in Google. And once you go to my website, you have to go under teaching and find 571, 572. So this will be the website of the course, and it is updated rather on a regular basis. So these are the two books that will be required. The first one is our notes from myself, and this will be updated. This is still in the writing process, so they will be updated on a weekly basis. And the second one is a very famous book of Serge Lang by Springer. I picked the third edition because that's available on the market now, but it doesn't really matter to me, whatever edition you have. So if you have an older edition, that's fine too. Okay, well, what will be covered in this course in very brief terms, and then I'll go in detail a little bit more about this. But in brief, algebra is mainly separated in four main parts. Well, group theory, ring theory, module theory, and field theory. So we will cover all these four parts rather in detail. So groups, rings, modules, and fields. I do expect that everybody who is in this class has some kind of exposure to algebra. I will not prove or go over what is considered undergraduate algebra, abstract algebra. So if you don't have a strong background, or if you don't know some of these things, or if you have taken this class a long time ago and maybe you have forgotten, I would suggest maybe these three books, which could be very nice books to look at: Abstract Algebra by Damit and Food, Abstract Algebra by Joe Gallion, and a classical book, Abstract Algebra by Herrnstein. Actually, there are two books by Herrnstein. One, I think, is called Abstract Algebra, and then the other one is Topics in Algebra. The other one, Topics in Algebra, it's actually quite nice, and it has very nice problems. Maybe it's not so easy to find those books, though, Herrnstein's books, since they have been published a long time ago. And there are many other books in algebra. Okay, the grading of this course will be done in the following scale. So the homework will consist of 20% of the grades, the two midterms, 20% each, and then the final exam, 40%. Grades will be computed using the following formula, at least for the Auckland University students, and for students who are taking the course in other universities, according to their scaling, their grades. But for Auckland students, it will be T, where T is the total percentage that you get out of 100 from the score, from the tests and the homework. T minus 35 over 15. So Auckland has this scale of 0 through 4.0, 4 being the highest grade, and so we will use this formula. The midterms are scheduled for this week. So the first one is October 3 to 7, the second one November 14 to 18, and the final one will be sometime in December, probably December 8 to 15. I will let you know exactly when that is. Well, there are a few other things here that you might want to look at. Most of them are either final exams or old stuff from the semesters, and they have problems, and I'm keeping them there for those of you who want to maybe look at them and solve some of the problems there. Okay, so let's just see if we can continue now, maybe, and start discussing a little bit in more detail what will be covered in the course. By the way, this is a calendar of the course. These are the lectures, how they will be delivered, and here you have the homeworks, how they will be given and when they are due. So now let's just get started a little bit on what will be covered on this course. So this is actually the PDF file or the topics that we will cover here, and this is basically, here, let me get rid of this, the table of contents for this. So the first part is groups. Very briefly, I will go through groups, definitions, and homomorphisms. This will be maybe one lecture or two or something like that. So I will mention cyclic groups and subgroups and normal subgroups and so on. Then the second chapter is rather important because I don't know how much of this is really done in the undergraduate level, but it depends where you took the course and who taught it. But I will discuss in detail group actions because they are very important, not only in group theory, but also applications of group theory to other branches of mathematics. So group actions, and that will be conjugacy classes, conjugacy in SN, which is quite important, group actions on sets, the class equation, Cayley's theorem, and some information about P groups, automorphism groups, and then finally the Sula theorem. Okay, after we do this, we'll get to normal series and solvable groups. Now all you know already what a normal subgroup is, but then we'll discuss what is a normal series, the Schreier's theorem, what are solvable subgroups, a little bit of nilpotent groups, and the central series of the groups. And so most of the problems we will do here will be kind of, well, how can we show that a group is solvable, and say a little bit at the end about the so-called simple groups and maybe a few remarks about the classification theorem and so on. Then quite an important chapter here will be the finite abelian groups. This is quite important for a lot of reasons, applications to number theory and algebra and other areas of mathematics. I meant applications to number theory and algebraic geometry and other areas of mathematics, and we have the so-called fundamental theorem of abelian groups, which tells us basically how an abelian group can be written. Okay, representation theory, and we'll do a little bit, not much, maybe one or two lectures here in the representation theory, sorry about that, in representation theory of groups. And then toward the end of this, maybe I introduce you to some of the things that maybe you can do in GAP. I mean, it is actually very easy nowadays for group theories or even for a non-group theory to use a lot of group theory, and this is made possible because of things like GAP and things like that. So yes, this could, we will do a little bit of that. And then the second part is a little bit more special topics in group theory. One of them is extensions, so extensions of groups, and cohomology, so we will do a little bit of that. And then maybe this is a chapter that I have not written yet, maybe a little bit more on linear groups. This is a very exciting and interesting area that goes into a lot of different branches of mathematics. Well, ring theory, you should have seen a little bit of ring theory in undergraduate mathematics. So it's the first chapter is basic ring theory, so introduction to rings, matrix rings, ideals, nil radical, Jacobson radical of rings, ring of fractions, Euclidean domains, and PIDs and UFDs, and so on. And then one of the most important rings that there is the ring of polynomials. So how can we make polynomials into a ring, and what kind of properties this ring of polynomials has? And we will look at things like Hilbert basis theorem and some things about polynomials which could be extremely useful, like symmetric polynomials and discriminants and so on. Now, initially, I'm planning that this is where the first semester ends. Uh, we'll see. Okay, we'll see how we proceed. Now, modules, this is really done in detail in a class that, in a commutative algebra class, but we will touch a little bit about this stuff here. So we will define what a module is, what are free, projective, and injective modules, exact sequences, tensor products, flat modules, and things like that. And then as part of this, we'll discuss a little bit of Noetherian rings and Noetherian modules, actually, and this is quite important. And then as a special case of modules are vector spaces, which are modules defined not over a ring, but over a field. And so this is a part of linear algebra that you already know some stuff. So I here, as the idea of chapter 14 is not to really do linear algebra in detail, but instead to on touch upon some topics or things that you might not have seen in a linear algebra, undergraduate linear algebra course. Okay, so then the last part of the second semester will be the so-called field theory. Field theory is very nice and extremely useful for things like cryptography and coding theory, and all the arithmetic is number theory and so on. So all the arithmetic is done over fields. So really, that's where you really understand algebra, and that's where you can use algebra in areas like number theory, algebraic geometry, applied mathematics, cryptography, coding theory, communication theory, and so on, when you know fields. And so we will do basic field theory, and then we will discuss in detail finite fields. And then we will discuss a little bit some old classical problems that you probably have heard from high school, namely geometric constructions, algebraic equations, and things like that. Then we will get to Galois theory. You know that one of the main problems in algebra is really how to solve equations. And you probably have heard the stories that there is no formula for a degree 5 equation or above. Well, we will discuss this in detail. How can we solve these equations when there is a formula and when there isn't one? And what can we say about this? And this is what Galois theory is all about. You probably have heard of, because of the Évariste Galois, who has quite a interesting story about his life also. So Galois theory, it is considered by many as one of the jewels of mathematics. It's really nice and very elegant, and it is really algebra in its best. So we will see a little bit about that. How do we find the Galois group of polynomials? How can we, by Galois group, determine whether a polynomial has a formula, can be solved or not, and so on. And you know, solving equations, polynomial equations, it has been one of the main central problems of mathematics. All right, so that basically will kind of wrap up the course, and I intend to actually do this in detail. Now, about the status of these lecture notes? Look, they are not perfect, but I will try to get them in as much complete shape as possible when I actually lecture on these things. So we will stop here and continue with the first lecture of the course, groups and their homomorphisms. So let me stop right now.